Hello my dear lovely people. Today we are going to start about another new topic of the fundamental physics is called as the scalar vector and the tensor. This is a very important topic in the physics because everything you are dealing with in the physics is only of three types, either scalar or vector or the tensor, any quantity. Now we are going to introduce about these three topics, these three entities, that is the scalars or vector, or it may be the tensor. First, I'll try to introduce you to the scalar one. The scalar one is any quantity. Later on, we have derived magnitude of any quantity. Maybe it's about a length. It's about a meter. It's about 2 seconds, or it's about your velocity, like 5 meter per second, whatever it may be. It is dealing with one of these. It all will belong to one of these three entities. That is one the scalars or vectors or the tensors. First, we will go to the scalar. What the scalar is? Scalar means everything we are dealing with, there is no concept of direction in it. Direction means no one will ask you to which direction it is giving you. All is about the magnitude. Suppose I am telling you I have 20 joule of energy in my muscles. Now, is there someone who will ask me to which direction? Either it is eastward or westward? No, it is only 20 joule of energy. I have 50 kg of weight. I mean 50 kg of mass I have. No one is going to ask me to which direction I have the 50 kg of mass. There is no concept of direction. There is nothing else than the magnitude. 50 kg, that's it. And this is known as the scalar quantity. This is a scalar quantity which is associated to any physical magnitude or physical quantities is only having a single one and only term is known as the quantity or the magnitude. Nothing else than that. So the scalar quantity is only magnitude, no direction. I have written here, you can see, and you can see the example of the scalar quantity. Yes, there are many examples. There is the mass. I said I have 20 kg of weight. Pressure, 2 atm pressure. My deodorant contains suppose 1 kg per square centimeter. That is the pressure. No direction. Energy, etc. Whatever the term you have, that is called the scalar quantity. At only one term, that is the magnitude of the quantity, is known as the scalar quantity. In the tensor version, it is also known as the zeroth order tensor. By the zeroth order tensor, I mean you can say the scalar, vector or tensor, whatever you may be. All the scalar and vector form is just a special type of the tensor. I will talk about it later. This is known as the zeroth order tensor. The tensor has a rank, maybe first order tensor, maybe second order tensor, maybe third order tensor, maybe zeroth order tensor. So this, according to the rank of this tensor, the zeroth order tensor is known as the scalar. The first order tensor is known as the vector, and the second, third, and onwards is known as the tensor simply. So the scalar term is known as the zeroth order tensor. Then we'll come to the vector. Now the question is, suppose I am driving my bike with the 50 km per hour. Now someone will say, to which direction you are driving to? Where you are going? Maybe I can say, I am going to the north, I am going to the east. That does not mean, this means there is a question mark of the direction. This is called as the vector quantity. What vector quantity? Suppose here I have a thing. Suppose, I don't know, maybe suppose any quantity is here, and as I said, this quantity, this much of quantity is associated with this point. Someone will suddenly ask me, when I will tell that quantity, if I have not mentioned its direction properly, he will suddenly ask me to which direction it is. I can say, well, this is in this direction. This may be in this direction, whatever it may be, but there is a concept of direction it is. So this quantity have two entities, means two concepts. One is the magnitude, how much it is, and second is the direction, to which or which word it is, means acting to which direction. Maybe I have a coordinate system here. Suppose I draw a coordinate system. Let me give it like this. Suppose I draw a coordinate system. Here is the x-axis, here is the y-axis, and here is the z-axis. Now I can say some component it is 1 times in the y direction, 3 times in the x direction, and minus 1 times in the z direction. So these are the, I can specify its direction at instant by saying that this is a vector quantity. So vector quantity is known as the first order tensor. Any vector quantity you say, it is known as the first order tensor because it has a single direction. This doesn't mean it has a single direction, that is the tensor. It has a direction. It has no direction, that is known as the zeroth order tensor. It has a one direction, that is known as the first order tensor. And example, you can say the velocity. Little bit before I was discussing about its velocity, its momentum. I am driving at 10 meter per second. I have 30 kg weight, so 300 meter per second times kilogram. That is known as the momentum. Now suddenly has to which direction you are driving to. That is known as the momentum. So momentum is a vector quantity. Remember one thing, when a scalar is multiplied with a vector, that gives you a vector. Exactly same concept is driven here. When a mass, which is a scalar, is multiplied with a velocity, that is a term which is a vector, means mass is scalar and vector is vector. Velocity is a vector, and then multiplied to produce a momentum, that is also a vector. The notation is that the vector quantity, all the vector quantity, the velocity v, the momentum p, the acceleration a, forces f, displacement s, all are represented with an arrow sign on the top. Is denoted as, that is associated with a direction over here. Well, the momentum is also a direction, having a direction, acceleration having a direction, force having a direction, displacement having all the quantities. Any vector quantity you may write. Always you need to specify direction. Sometimes some professors or some teacher gives like this type partial arrow, or some of them are giving no arrow. That's just a single line. All this denotes a single entity, single thing. That is, it's a vector. So this is a very important concept. Before I go to tensor, I will do it again, that when a scalar is multiplied with a vector, that gives a vector. Remember this. Okay, let's come to the tensor. It's a little bit tricky one. What is the tensor? Tensor is not like a vector. Tensor is not like a scalar. It's completely different. First basic concept of tensor, when you are going to introduce it, is known as, suppose here look, I have a coordinate system and I put a vector in it, and if I will rotate the coordinate system, suppose this is being 2 times in the x direction and 1 times in the y direction, and suppose, I don't know, maybe 3 times in the z direction. Then suppose I rotate the coordinate system by angle theta, all these components 3, 2 and 1, everything will change. This is the property of a vector, that when your coordinate system is rotating, or when a coordinate system is shifted or rotated or shifted, whatever you may change, apply operator to it and rotate it, or do it anything, whatever you want to do, the component will not remain same, it will change. This is the property of the vector, where the reverse happens in the properties of a tensor. Tensor, in case of a tensor, you can say have many tensor. One is a very famous tensor, is the stress tensor. You will learn in your mechanical engineering or in your higher mechanics, you will learn this. There is called a stress. Also we will learn it here, but no concept of tensor here. The stress is itself a tensor. Another one is a very famous one, is known as the Kronecker delta. It's an easy one. This is called as the identity matrix. We'll learn it. This is actually, tensor is a very huge topic. Then another one is called as a metric tensor. This tensor is in your general theory of relativity of Albert Einstein, and this is known as the small g mu nu. You can see the very famous equation g mu nu. Another one is called Riemannian tensor or the Ricci tensor. Ricci tensor is r mu nu. This is actually a correction in your spherical coordinate system. Actually, tensor has a huge application in your advanced physics. So this is very fundamental thing. Remember that when a tensor is such a quantity that when you are putting in a coordinate frame and rotating your coordinate frame accordingly, whatever you want to do, the component of the tensor will remain unchanged. This is a very crucial point, where the vector, if you rotate your coordinate system, all the component, all this is the x magnitude, y magnitude, the z magnitude, everything will change. But in a case of a tensor, it may be second order, third order, up to you, whatever order you are doing with your jobs. Everything, when you are rotating a coordinate system, its component will adjust itself to remain the entire thing constant. This is the tensor, and this tensor, I have no specific concept to represent it, like a vector or like a, I don't know, maybe arrow mark, maybe double arrow. I have no concept to represent it. It is actually a virtual thing. So they have drawn a cube here to represent that it is a multidimensional concept, and you can say it is a combination of vectors, scalars, everything is inside this. This is actually a concept of higher dimension. I cannot able to represent it on the backboard, but I can feel you, I can give you the feelings that tensor is such a things. Actually it is always, it is form a matrix. So the Kronecker delta, I was saying that it is identity matrix. What it means, the Kronecker delta is equal to identity matrix 1 0 0 for 3-dimensional cases, 0 1 0 0 0 1. This is called the Kronecker delta. Means delta ij, sorry, so delta, I think I can visualize it, or yes, delta ij is equal to 0 when I is not equals to j, delta ij equals to 1 when I equals to j. This is a very famous tensor in your mathematics, is known as the Kronecker delta. I can give you a visualization of the stress tensor. Just wait for a couple of seconds. I am trying to give you a visualization of the stress tensor. I hope I can do it easily. Suppose, consider a beam. A little bit mechanical term here. Okay, suppose consider in simple word, suppose this is a rod, okay, and this point is fixed to a wall, and I am applying 30 kilonewton of force in this cross sectional area. This is not pointed one, this is all this cross sectional force having at the end, and 30 kilonewton is applied on the entire cross sectional area. Suppose its area is noted as A. Now my question is, what about the force at this point, single point inside the rod or inside the beam? Suppose I ask you, what about the force internal resultant loading at this point? Now what can I answer? Means, you know, at this point there is a reaction to this side, there is a reaction to this side. Suppose it is, this force is not vertical, means not horizontal, suppose like a tilted one, like this direction. So there will be a component in this direction, component in this direction, everything. So let's magnify at this section. You can visualize the tensor little bit, not perfectly. Suppose you have a beam like this, and I am interested to at this point. So I can say stress equal to force per area of cross section, or force per unit area. So at this point I have to consider a little tiny plane, and I have to consider a single line of force at here, so that I have a force of magnitude, let it be R. I have to consider a net resultant force R at this point, and I have to consider a little tiny area of cross section. Is it visible? Oh, wait a second. Suppose this is a beam, a cross section of the beam. Suppose this is a cross section of the beam. At this point I am interested to observe at this point. So for this point I am observing here, I am interested to calculate the resultant loading at this point. So I need to find out the stress at this point. So for stress I need an area and I need a force, because stress equal to force per unit area. So I need a force. I have to give you the arbitrary force. The force is maybe like this. It's not sure that it is horizontal in the x-axis. in the direction of that's not, it may be arbitrary in any direction, and I need to fix a plane or a little tiny surface on it. So I fix a surface on it. Now the question is, how much degree of freedom have this force has? Means I have fixed this force along the x-axis. Is it certain that it will be fixed on the x-axis? No. I can fix it on the y-axis. I can fix along the z-axis. I can fix along any linear combination of axes. No, I'm not happy with this. I can say that force is like this. Force is any direction. So how much degree of freedom the force has? 3 degree of freedom. How 3? I can take x-axis, put y and z value 0. I can take z-axis, put x and y value 0. I can take y-axis and put x and z as 0. Or I can take any axis. I take x is equal to 1, y equal to some number maybe 3.5, z equal to 13.5. So there is 3 degree of freedom of this force in your 3-dimensional coordinate system. I am not interested in the 4-dimensional or any higher dimensional order. I am interested in the 3-dimensional order. This is a cube of 3 dimensions. So everything I am doing here the 3 dimensions. That's why there is 3 degree of freedom of this force. Now I am interested in okay, I fixed one thing, that is the force. I am happy with this line, and I fixed this line which is having 3 degree of freedom, and I fix my force, that is, this is my final force, and I fixed it. Next thing what I need, that is a surface. How to define a surface? Surface is something that passing through a point and having a fixed normal. In other words, I can say there is I can construct a surface after which basically I need a single point through which the surface is passing, and now this point I can rotate my surface at any direction. You can see this point, a tip of a pen, I can fix it, and I can rotate my surface at any direction here. So to fix a surface, I need this point, and I need a single normal vector, fixed normal vector to it, for which the surface will be fixed. Similarly, to fix a normal vector here, you need another vector. So like I put another normal vector n to this surface. Now consider how much degree of freedom the n has. N is itself a vector. You know, it's a normal vector to the surface. This is not the force vector. Force vector is something different, and this, so to this surface here is a single normal vector. The normal vector has itself 3 degree of freedom. You can say n hat is equal to some component, I don't know, maybe 1.5 times in the x direction, and 2.3 in the y direction, and 5.6 in the z direction. So this is the n hat, and the n has itself a 3 components, 3 degree of freedom. So n has 3 degree of freedom. Can you say how much degree of freedom the entire stress has? Because stress is equal to force over area. So force has 3 degree of freedom, area has 3 degree of freedom, total degree of freedom is equal to 3 times 3 is equal to 9. This is the simple permutation and combination. If you have 2 boxes and you can fill this as 3 ways, you can fill in the other 3 ways. So how much the total number of ways in which you can fill the box? That is the 9. So there is a 9 degree of freedom of stress here. So in the 3-dimensional cases there is 9 degree of freedom. In the 4-dimensional cases there is 16 degree of freedom. You can see. So that's why I was telling that this tensor, the stress tensor, Kronecker delta, metric, Ricci, whatever the tensor, or Christoffel symbol, whatever the tensor you have is a multi-dimensional concept, and the tensor itself changes its component to fix. Tensor itself changes component when you are rotating the x, y and z axis. The total tensor, the stress is independent of your choosing of your axis. You know, suppose there is a beam and I am acting a force at any point, the force should be a constant, that the stress should be constant. Is it dependent on the rotation of the plane, rotation of the axis? No. So the total tensor is remains constant, and the tensor itself changes its component to, or adjusts itself to its component to keep the total things constant. So you can see the vector is also a single part of a tensor, in which there is just magnitude and there is a direction, there is a fixed direction. Scalar have nothing excuse me scalar have nothing in it, that is a single dimensional, no dimension, single entity concept, and the tensor is a multi one. Actually this is so much simple, this is not so much simple. There is a lots of mathematics, there is a partial derivative, and you can see the Kronecker delta, Ij. There is a tensor, this is called the your Kronecker delta. There is a stress tensor, the metric tensor is denoted as the Z mu nu, Ricci tensor is R mu nu. There are much more derivative and much more partial derivative terms in the tensor. This is a much more higher concept, we will learn it later. Just for your physical starting, I give you a picture to which visualize this is the tensor. Okay, so you have understand the scalar, you have understand the vector, and you have understood the tensor. At the next video we will do little bit algebra on the vector. Scalar is nothing, scalar you can say addition of scalar. Suppose there is the addition of scalar, suppose 2 joule of energy plus 3 joule of energy gives you 5 joule of energy. Simple addition, one first standard primary school calculation here, nothing more, no huge difference, means no new thing here. You can simply directly go to the number and just add this and you will get the final result. But in case of a vector, the things changes. We will learn the next video or the next lecture. We will learn the how to add the vector, how to subtract, how is the product, the multiplication. You can simply take the multiplication of the scalar, just multiply these two numbers and you get another number. Okay, so that's it for today. Next video we will go for vector algebra and vector mathematics. Thank you for watching, and if you like this video, please share and subscribe my channel, and thanks for today.